Hello, my name is George Savic. In my previous two videos, I showed you how special relativity contradicted both quantum mechanics and general relativity respectively. In this video, I am going to give you the full theory of quantum relativity. I am going to show you how quantum relativity resolves the contradictions I mentioned in the previous two videos by showing you some thought experiments and equations that hopefully will not be too overwhelming for you. To start at the beginning, let us agree on the fundamentals of the three separate theories in the spotlight. With special relativity, there are only two assumptions made. The first assumption is that the laws of physics are always the same for all observers in every frame of reference, whether moving with a constant velocity or not moving at all. The second assumption is that the speed of light in a vacuum is a constant for all observers, whether the observers are moving or standing still. In quantum mechanics, there is an uncertainty principle. In its most basic form, the uncertainty principle states that an observer can know the position of a particle or they can know the velocity of that particle, but they cannot know both the position and the velocity of that particle. When it comes to quantum relativity, I assert that there is only one assumption and only one golden rule. The one assumption in quantum relativity is that distance, time, and velocity are not dimensions. They are forms of entropy. They do not cause observable change in space. They are the observable change in space. The golden rule in quantum relativity holds that if two observers in two different frames of reference agree that any one of these three forms of entropy is an absolute universal constant for the both of them, then they must also agree that the other two forms of entropy are relative to each of them. The way that we can interpret this is by saying that if two observers agree that any one of the three forms of entropy is a law of physics, then the two observers must also agree that the other two forms of entropy are not laws of physics. So how do these three theories fit together? Well, the second assumption of special relativity is directly connected to the one assumption in the golden rule of quantum relativity, which in turn are directly connected to the uncertainty principle of quantum mechanics and the first assumption of special relativity.
Oh, now, look here, George. If you've gone out of your head, I forgive you. But if you've made us waste all this time listening to you talk so much...
No, Doctor. You're here as witnesses. To see, not to listen.
To see? What?
The experiment I am about to perform.
Let's imagine that there are two observers, one on a train in a moving frame of reference and one on the ground in a non-moving frame of reference. We know that both of the observers will see that it is the other observer who is the one that is moving. Therefore, it is always the other observer that is experiencing the time dilation, represented by the lowercase t bar, and the length contraction represented by the capital letter L. And if we agree that the train is moving at a velocity of 86.6% the speed of light, then we can say that both of the observers will measure that it is the other observer who is experiencing the 50% time dilation and 50% length contraction.
I'll explain how it works later. It's all relative.
Now let us imagine that there is a particle of light that is moving between two poles, which are 300 million meters apart. According to the second assumption of special relativity, both of our observers must measure the speed of light to have the same value. Let's test that assumption.
Oh, that's how it is?
Oh, that's how it is.
Okay.
For the stationary observer, the distance between the two poles is 300 million meters, and it takes the particle of light 1 second to travel that distance. Therefore, the stationary observer calculates that the speed of light in his frame of reference is 300 million meters per second. The observer on the moving train is experiencing 50% time dilation in his frame of reference. But from his frame of reference, it is the stationary observer and the two poles that are moving. So, relative to the observer on the train, it is the two poles that are experiencing the 50% length contraction. And as a result, they are only 150 million meters apart. Therefore, the moving observer also calculates that the speed of light in his own frame of reference is 300 million meters per second.
Huzzah! Oh, this is fantastic!
There are three things that stand out in this thought experiment. First, special relativity's first assumption is proven to be correct. The speed of light is indeed a constant for both of the observers, even though the observers are in different inertial frames of reference. Second, the uncertainty principle of quantum mechanics is also proven true. We can see that both of the observers agree on the velocity of the particle of light, but they disagree on the position of the particle of light between the two poles. In other words, they disagree on the distance between the particle and the two poles. And third, the golden rule of quantum relativity is proven to be true. Because both of the observers agree that the velocity of the particle of light is a constant for the both of them, they also agree that distance and time are relative to each of them. Let us reimagine the parameters of the last thought experiment. And this time, let's say that the two observers agree that the distance between the two poles is exactly 300 million meters, always. Would the two observers still agree on the velocity of light? For the stationary observer, nothing has changed. Therefore, he still calculates that the speed of light is 300 million meters per second. The observer on the moving train is still experiencing 50% time dilation in his frame of reference. But this time, the moving observer agrees with the stationary observer that the distance between the two poles is 300 million meters. Therefore, the moving observer calculates that the velocity of light in his frame of reference is now 600 million meters per second. We see four things that stand out in this thought experiment where we change the premise of the laws of physics. Firstly, the golden rule of quantum relativity is proven to be true. Both of the observers agree that the distance between the two poles is a constant for the both of them. Therefore, they also agree that time and velocity are relative to each of them. Secondly, the uncertainty principle of quantum mechanics is also proven true. We can see that both of the observers agree on the position of the particle of light between the two poles, but they disagree on the velocity of the particle of light. Thirdly, it's obvious at this point that the golden rule and the uncertainty principle are being observed. But what about the second assumption of special relativity? Well, because we started the thought experiment with the premise that the two observers now must agree on the distance that light travels, the second assumption of special relativity must now conform with the golden rule and say that observers must always agree on distance and not agree on the speed of light. And fourthly, because the values for the velocity of light are no longer the same, we cannot use the same letter to represent them. That being the case, let's designate the letter X for the velocity of light measured by the moving observer, and let's keep the letter C for the velocity of light measured by the stationary observer. This way, we will be consistent with the previously measured velocity of light. Let us now reimagine that thought experiment, again changing the premise of the laws of physics. This time, let's say that the two observers agree on time. What would the two observers measure for the velocity of light now? Again, for the stationary observer, nothing has changed. Therefore, he still calculates that the speed of light is 300 million meters per second. The observer on the moving train will observe 50% length contraction for the two poles in his frame of reference. But now the moving observer will agree with the stationary observer on the measurement of time. So the moving observer calculates that the velocity of light in his frame of reference is now 150 million meters per second. Because the values for the velocity of light are not the same, we can designate the letter Z for the velocity of light measured by the moving observer, and keep using the letter C for the velocity of light measured by the stationary observer. This way, we are still consistent with the previous two measurements for the velocity of light. Now, it may appear as though there must be a contradiction to the laws of physics, but there is absolutely no contradiction at all.
Well, I wish you'd explain it to me sometime, Buster.
We can prove this by taking, for example, the two equations E equals mc squared and m equals E over c squared. We know that both of these equations are laws of physics. One equation tells us how much energy mass has, and the other equation tells us that mass increases when we add energy to it. Let us now imagine that the moving observer has a mass with him on the train. Relative to his frame of reference, he is not moving. Therefore, he calculates that the energy for the rest mass on the train is exactly E equals mc squared. But relative to the stationary observer, the mass is moving, and therefore the stationary observer calculates that the energy for the moving mass is exactly E equals m plus E over c squared times c squared. Straight away we notice two problems. The first is that the two observers disagree on the equation to calculate the mass. And the second is that the stationary observer cannot use the letter E to simultaneously represent both the answer and the variable within the same equation. Let's fix the second problem first. Since we know from the equations E equals mc squared and m equals E over c squared that mass and energy are equivalent, it means that energy is mass in joules and mass is energy in kilograms. From this, we can recognize that the letter E for the variable within the stationary observer's equation represents what we can refer to as energy, which we measure in joules. The stationary observer's equation implies that the answer letter E on the left side of the equation is clearly greater than the variable energy letter E on the right side of the equation. This means that the answer is associated with energy while simultaneously being greater than the energy. This being the case, let us agree that the answer for both of the observer's equations is something we can refer to as stamina, represented by the Greek letter sigma, and which we also measure in joules. If we now agree that energy equals mass times the speed of light squared, then we must also agree that stamina does not equal mass times the speed of light squared. This is because the letter m is rest mass for the moving observer and relativistic mass for the stationary observer. If we can agree that weight is relativistic mass, represented by the Greek letter omega, and we agree on the divergence between relativistic mass and rest mass, then we can agree that energy equals mass times the speed of light squared, and that stamina equals weight times the speed of light squared. In this way, the energy of the rest mass calculated by the moving observer equals the stamina of the relativistic mass calculated by the stationary observer. In essence, the fundamental nature of stamina is to energy what the fundamental nature of weight is to mass.
Because look, there's some next level shit going on around here and I'm with that. But before y'all get to beaming me up, it's a couple things I want you to understand. First off, you chose me, so you recognize the skills.
If we can agree that 1 over 1,000 kilogram is 1 gram, and 1 over 1 million kilogram is 1 milligram, and we know that c squared is 300 million times 300 million, which equals 90,000 trillion, then let us agree that 1 over c squared kilogram is 1 gem, where gem is an acronym for joule equivalent mass, which literally means that a gem unit of mass is directly proportional to the joule unit of energy. The purpose for the gem unit of mass is to help make a distinction between stamina and energy, while simultaneously keeping the equivalence of mass and energy. The way that we achieve this is that we not only agree that energy is 1 joule equals 1 watt times 1 second, but we also agree that stamina is 1 gem of mass times the temporal reference equals 1 joule of energy times the same temporal reference. In this way, Stamina is connected to energy in exactly the same way that weight is connected to mass, while simultaneously being distinct from energy in exactly the same way that weight is distinct from mass. Not only does this not contradict the equivalence of mass and energy, but it also implies that there is an equivalence between weight and stamina. Looking at the equation of E equals mc squared as mass and distance squared over the same period of time means that stamina literally is a quantity of mass and energy over the same period of time. In simpler words, stamina is me over t.
You've given a most lucid explanation and all that, but I'm afraid I don't quite understand.
Walter, look, there are many things in this world you don't understand, aren't there?
Yes, quite a number.
Well, you don't refuse to believe in them because of that, do you?
No, not if I can see the proof with my own eyes.
Good, Walter.
Going back to the first problem now, we know that the moving observer has 3 different values for the velocity of light. Therefore, we can conclude that he also has 3 different stamina equations to measure the mass on the train. But the moving observer must correct for each value of the velocity of light squared by including the temporal reference to his equations, represented by the Greek letter psi, thereby completing the 3 stamina equations. The temporal reference is an equation that calculates a frame of reference based on the value of the inertial or gravitational velocity that is the basis for that frame of reference. The rule of thumb with velocity is the inertial and gravitational velocity is always directly proportional to the velocity of light that is used. Given that these 3 stamina equations are laws of physics, and given that the second assumption of special relativity states that the laws of physics are the same in every frame of reference, then both of the observers should be able to use these 3 equations respectively when we redo the last thought experiment, and the moving observer should get the exact same stamina value for the mass on the train that the stationary observer gets. If we now apply real numbers to the values relative to each observer, then we know that both of the observers agree that the velocity value in the temporal reference for the 1 kilogram mass on the train is 86.6% the velocities of light x, c, and z, respectively. When each observer incorporates the temporal reference value to the respective stamina equation, he will get a value for the stamina that is identical to the value that the other observer gets.
I bring this particular matter to your attention because it illustrates something. That when a law is right, it can be used to find another one. That by having confidence in this law, if something is the matter, it suggests perhaps some other phenomenon.
How does gravity fit into this picture? According to the current understanding of physics, weight is a gravitational force that is acting upon a mass. This is expressed in the equation gravitational force equals mass times the gravitational field strength. This gravitational force is measured in units of newtons. Since we know that the Earth's gravitational field strength is 9.81 meters per second squared, then we can calculate that the weight of a 1 kilogram mass on the surface of the Earth is 9.81 newtons. And since the gravitational field strength on the Moon is 1.625 meters per second squared, then we can calculate that the weight of a 1 kilogram mass on the surface of the Moon is 1.625 newtons. From this, it does appear as though the weight for a 1 kilogram mass is 6 times heavier on the surface of the Earth than it is on the surface of the Moon. The question that I am proposing is, does a 1 kilogram mass really weigh 6 times heavier on the surface of the Earth than it does on the surface of the Moon? To find the answer to that question, we need to know 2 things. What is the x-value speed of light in our frame of reference? And how do we find the temporal reference for the Earth and the Moon? We already know that the measured c value for the speed of light is 300 million meters per second. But now we need to identify if this measured value is the velocity of light that is fundamental to our frame of reference with the value of x, or if it is the true speed of light, which is the value of c. To help us find the answer to this question, we can use the quantum mechanics equation that calculates the energy of light and the three equivalent equations of quantum relativity that do the exact same thing. By matching the equations that appear to be the same, we can conclude that the 300 million meters per second velocity of light that we measure on the surface of the Earth is the value x. That is the value for the velocity of light that is fundamental to our frame of reference, and not the value of c, which is the true speed of light. Now, how do we find our temporal reference on the surface of the Earth? Well, for that, we need to find the gravitational time dilation on the surface of the Earth. And the Earth's gravitational time dilation is calculated by using the Earth's escape velocity. We can calculate the Earth's escape velocity by using one of a number of equations that I know of. For this example, let's just use the simplest one of the four equations listed here. This equation tells us that the Earth's escape velocity equals the square root of 2 times the Earth's surface gravity times the radius of the Earth. This tells us that the Earth's escape velocity is 11,189 meters per second. We can now incorporate this gravitational velocity into the temporal reference equation to find the temporal reference on the surface of the Earth. Using the Earth's temporal reference, we can now calculate the true speed of light with the value c. And when we do this, we find that the true speed of light is just under 300 million meters per second. Using the stamina equation with the value c and adjusting for the Earth's temporal reference, we get a value for the stamina of a 1 kilogram mass that is on the surface of the Earth. Using the same stamina equation, this time adjusting for the Moon's temporal reference, we get a value for the stamina of a 1 kilogram mass that is on the surface of the Moon. Straight away we notice that the 1 kilogram mass is nowhere near 6 times heavier on the surface of the Earth than it is on the surface of the Moon. This means that the definition of weight as a force acting upon a mass, which we measure in newtons, should not be considered as an accurate definition for weight, because it doesn't work for every gravitational temporal reference. If anything, we should define the precise meaning of weight as relativistic mass, and that would explicitly illustrate that weight is mass with extra energy due to a specific inertial or gravitational temporal reference.
Confused? After I reveal my tale to you, everything will become crystal clear.
For example, let's imagine that there is a mass on the surface of the Earth. Let's accept the premise that weight is a force. Then, given that force equals the mass times the surface gravity, and given that gravity on the surface of the Earth equals 9.81 meters per second squared, then we accept that a 1 kilogram mass on the surface of the Earth has a weight of 9.81 newtons. And because we know that work equals force times distance, therefore we must also accept that it will take 9.81 joules of energy to move a 1 kilogram mass 1 meter away from the surface of the Earth. Now let us imagine increasing both the mass and the radius of the Earth until we have a supersized Earth that still has a surface gravity of 9.81 meters per second squared, but now with an escape velocity that is the speed of light. For lack of a better description, the surface of this supersized Earth is now an event horizon. If we still accept that weight is a force that equals the mass times the surface gravity, then we must also accept that the weight of a 1 kilogram mass on the surface of this supersized Earth should still be 9.81 newtons. That means that we must also accept that it will still take 9.81 joules of energy to move the 1 kilogram mass just 1 meter away from the surface of an event horizon of a black hole. But if we accepted such a premise, we would be totally wrong! We know this because with an escape velocity that equals the speed of light, the 1 kilogram mass on the surface of an event horizon would have a relativistic mass of infinite kilograms. This would mean that on the surface of the supersized Earth, it will take an infinite amount of energy to move the 1 kilogram mass any distance at all from the surface.
What have the humans done?
I don't know.
Explain! Explain! Explain!
Given this fact, we can argue that the equation force equals the mass times the surface gravity can be understood to mean that this type of force describes a gravitational mass, not weight. If we agreed that weight is relativistic mass, and we understand that relativistic mass is mass with extra energy, then we can say that if force equals the temporal reference times the mass times the surface gravity, then that can be understood to mean that force is a gravitational mass with extra energy, or gravitational relativistic mass. On the other hand, because we agreed that weight equals the temporal reference times the mass, then we can say that force equals weight times the surface gravity, and that can be understood to mean that force is a gravitational weight. And since we measure weight in kilograms, we can measure gravitational weight in newtons.
All right. Suppose what you say is true. What do you expect us to do with such a contraption?
Trust me on this one. You don't want to know. Audrey, don't tell him. You shouldn't have told me, but you did. And now I'm telling you, you don't want to know.
Let's assume for a moment that the speed of light has only one value, the value of c. Let us also assume that this value of c is a fundamental constant in every frame of reference. Now let us imagine an observer who wants to measure the energy of two identical particles of light. Because these are two identical particles of light, the observer will measure the wavelength of one of the particles of light and the frequency of the other. And as we well know, the wavelength of light times the frequency of that light will always equal to the speed of light. This means that the observer can use Planck's constant, represented by the lowercase h, times the speed of light with the value of c over the measured wavelength of the particle of light to get the value for the energy of light for both particles, represented by the letter E. Now let us imagine that this observer places the two particles of light on the surface of the Earth, which we all know to have a temporal reference where psi is a number value greater than 1, relative to that of the observer who is in a temporal reference where psi equals 1. Given that we know the relationship between length and the temporal reference, we can know that the observer, still in his original temporal reference, will measure an energy value for the two particles of light on the surface of the Earth as larger than the original energy value for the same two particles of light when they were in space. To explain this result in the simplest way possible, we can say that because the temporal reference on the surface of the Earth has a psi number value that is greater than 1, we ended up with two particles of light with shorter wavelengths, and as a consequence, they both have a higher energy value than they did in the original temporal reference.
Everybody got that? Good!
Let us now imagine a second observer that we will refer to as the primary observer, who will also measure simultaneously the energy of the two particles of light, along with the first observer, who we will now designate as the original observer. When the primary observer and the original observer are in the same frame of reference, we know that both of them will agree on the measured value for the energy of the two particles of light. This is because they are both in the same temporal reference, where psi equals 1. Now let us imagine that the primary observer goes to the surface of the Earth along with the two particles of light. We already know both the measurements and the reason for the measurements of the energy for the two particles of light that the original observer gets. It all came down to length contraction due to the temporal reference on the surface of the Earth having a psi number value that is greater than 1, while the original observer's temporal reference has psi equal 1. Focusing on the primary observer, who is now in a different temporal reference on the surface of the Earth, along with the two particles of light, where the psi number value is greater than 1. From his new frame of reference, there is no length contraction experienced by the two particles of light. And given that we assumed at the beginning of this thought experiment that the speed of light was going to be a fundamental constant in every frame of reference, therefore, we must conclude that the primary observer's measurements for the energy of the two particles of light must be exactly the same as they were in his previous frame of reference where psi equaled 1.
That's not possible.
Let's agree to disagree.
We can see from this thought experiment that if the two observers must agree on the speed of light, then they must disagree on the energy of light. If we assume that the two observers must agree on the energy of light, then we should also assume that the two observers must disagree on the speed of light. Because they cannot agree on both the energy and the speed of light, that is what gives us the quantum aspect in this thought experiment.
Now just wait a cotton-picking minute.
How can the two observers disagree on the speed of light? The answer is obvious. The primary observer must measure the speed of light on the surface of the Earth as having a greater speed than the speed of light as measured by the original observer in space. We can refer to this measured greater speed as a velocity, and we can agree that the speed of light is always a constant, but the velocity of light is subject to the temporal reference. In other words, think of the relative difference between velocity and speed in exactly the same way that you think of the relative difference between stamina and energy, which is exactly the same as the relative difference between weight and mass. We already know that in the primary observer's frame of reference, there is no length contraction for the two particles of light. Then that should mean that the frequency of light is a constant as well. But frequency is a quantity of cycles over a period of time. And because we know that the temporal reference on the surface of the Earth is a psi number value that is greater than 1, then we should also know that the primary observer will measure time differently to the original observer. As a consequence of this, the primary observer will measure a different frequency value for the two particles of light. And because we agree that the wavelength of light times the frequency of that light always equals the speed of light, therefore the wavelength of light times a different frequency for that light will now equal to a different velocity of light. There must be a fundamental difference between speed and velocity, and it all comes down to the temporal reference. It becomes obvious now that even though the two observers must disagree on the speed of light, they both have correct measured values for the energy and the velocity of light relative to their respective frames of reference. And that gives us the relativity aspect in this thought experiment. And when we combine the quantum aspect and the relativity aspect together into a single theory, we end up with something that is the theory of quantum relativity. Because of the inertial and gravitational equivalency, which is implied in quantum relativity, this means that what is true for a gravitational frame of reference must also be true for an equivalent inertial frame of reference.
Well, that's a very entertaining story, but unfortunately real detectives have to worry about that little thing called evidence.
Let us imagine two stationary observers. Let us also imagine that one of them is standing on a laser pointer. When this laser pointer produces two identical particles of light, both of the observers will measure the same wavelength and frequency for the two particles of light. This means that they will agree on both the velocity and the energy for the two particles of light. Now let us imagine that the laser pointer and the observer who's standing on it are both moving in the direction that the laser pointer produces the two particles of light. From the stationary observer's frame of reference, the two particles of light, the laser pointer and the observer who is standing on it, are all experiencing length contraction in the direction of motion, given that they are all moving in the same direction. Because the two particles of light have a smaller wavelength now, they also have a higher frequency, but the velocity of light remains constant relative to the stationary observer. The smaller wavelength for the two particles of light means that they also have more energy than they did when the laser pointer was stationary. From the perspective of the observer standing on the laser pointer, it is the other observer who is moving and experiencing the length contraction. Relative to the observer who is standing on the laser pointer, the wavelength for the two particles of light is exactly as it was before. The only observable difference that the observer on the laser pointer measured is the higher frequency for the particles of light. This is because he is experiencing time dilation, and that affects how he measures frequency. As a consequence of this, the observer on the laser pointer measures both a greater velocity and more energy for the two particles of light. Again, we see that if two observers in different frames of reference agree on the energy for the two particles of light, then they must also disagree on the velocity of light. It is also important to note that the moving laser pointer does not produce particles of light with greater energy in the moving frame of reference. If energy cannot be created or destroyed, this means that when the two particles of light are produced by the laser pointer in a stationary frame of reference, they have energy. And when these particles of light are produced by a laser pointer in the moving frame of reference, they have stamina. For example, in the last thought experiment, stamina can be understood as energy with extra energy, in the same way that weight can be understood as mass with extra energy.
Finally, someone who speaks English. Is that what just happened?
Let's imagine that we had a goose in space that can only lay a golden egg with a fixed quantity of mass. When this goose lays a golden egg on the surface of the Earth, then the golden egg appears to have a greater mass than it did in space. But we have already established that the goose can only lay a golden egg with a fixed quantity of mass. Therefore, the mass of the golden egg on the surface of the Earth cannot be greater than the fixed quantity of mass which the goose can lay in space. This means that when the goose lays a golden egg on the surface of the Earth, the golden egg does not actually have greater mass. It has weight, and it is this weight of the golden egg on the surface of the Earth that is greater than the original mass of the golden egg in space.
But you're all going to have to listen up.
Because this is where it gets complicated.
Now let us imagine that this goose in space is a laser pointer in space that can only produce a photon with a fixed quantity of energy. When this laser pointer produces a photon on the surface of the Earth, the photon will appear to have more energy than it did in space. But we have established that the laser pointer can only produce a photon with a fixed quantity of energy. Therefore, the energy of the photon on the surface of the Earth cannot be greater than the fixed quantity of energy which the laser pointer can produce in space. This means that when the laser pointer produces a photon on the surface of the Earth, the photon does not actually have more energy. It has more stamina. And it is this stamina of the photon on the surface of the Earth that is greater than the original energy of the photon in space.
Oh, there is just one more thing, Lieutenant.
We know from the equation E equals mc squared that there is a principle of equivalency between energy and mass. That is to say, if we increase the mass, then that will directly result towards an increase in the energy. To observe this phenomenon in a dynamic way, let us merge two quantum relativity equations into a single equation which illustrates that mass is always a constant in any given temporal reference. Using this equation in conjunction with the equivalency equation, we can see that mass and energy are directly proportional to each other by c squared. If we now imagine that the mass equation is at a given distance from the surface of the Earth, that would mean that both the temporal reference and the x-value velocity of light have increased. But their simultaneous increase in value cancel each other out, thereby causing no change in the mass. Even if we place this equation on the surface of the Earth, whereby we increase the temporal reference and the x-value velocity of light even more, mass will still remain constant because the increased temporal reference and x-value velocity of light still cancel each other out. And we know from the equivalency equation that if mass does not increase, then the energy does not increase either. Regarding stamina, I stated earlier that it is defined as a quantity of mass times the temporal reference equals a quantity of energy times the same temporal reference. This is also an equivalency principle and is expressed by the equation sigma equals omega c squared, where omega is weight as defined by the equation omega equals psi m, which means that weight equals the temporal reference times the mass. Going back to our thought experiment, when we multiply both sides of the equation by the temporal reference, we end up with an equation that gives us the weight for a given quantity of mass. When we now move this equation closer to the surface of the Earth, we notice that because the temporal reference is now squared, this means that the increase in the temporal reference is no longer cancelled out by the increase in the x-value of the speed of light, the consequence of which now results in the increase of the weight. The closer the equation gets to the surface of the Earth, the more the weight increases. And we know from the equivalency equation that if the weight increases, then stamina must also increase. But we know from the other equivalency equation that mass never increases, therefore the energy never increases either. This explains what is happening in the previous thought experiment with the laser pointer. The laser pointer has a fixed quantity of mass, and it can only produce a photon with a fixed quantity of energy. When the laser pointer is on the surface of the Earth, it has an increased weight. The other consequence of the laser pointer being on the surface of the Earth is that it will now produce a photon with an increase in stamina. But the original mass of the laser pointer and the original energy of the photon never changes. Mass and energy are constant. Under given circumstances, when mass gains energy, it becomes weight. Likewise, when energy gains energy, it becomes stamina.
Will that answer your question?
Objection, Your Honor.
Overruled.
What it is, man. Dynamite.
So, is there a difference between mass and weight? You tell me.
You want answers? I think I'm entitled. You want answers? I want the truth! You can't handle the truth!
This brings us to our final question. What does all of this have to do with anything?
I really don't have, time to bat this around. I'm kind of on a schedule. I got plans for August. Okay, I need an answer, now.
You might be surprised to hear that it has something to do with time. We've all heard how time can speed up or slow down.
It turns out, time itself can speed up or slow down.
Well, you see, that's not entirely correct.
Lies. Oh, lies!
According to the laws of chronodynamics, it would be more accurate to say that time can speed up and slow down.
No kidding.
And remain constant.
Oh, it's so stupid. What?
Simultaneously.
serious?
This should come as no surprise to anyone, since we have already seen at the beginning of this video that light can speed up and slow down and remain constant simultaneously. And we agree that there is a direct connection between the speed of light and time. But what if this direct connection is actually an equivalence between them? Then this would imply that if the speed of light is an absolute universal constant that is relative to an observer, therefore time must also be an absolute universal constant that is relative to an observer.
Great Scott!
That was just a taste of the nature and mechanics of time according to the laws of chronodynamics.
You want a taste?
Pardon me?
There's your taste.
That's my taste?
Wait for Echo.
Quantum relativity was originally just a very small part of a much larger theory that I like to call chronodynamics. When I first started scripting the video for quantum relativity, I never imagined that it would end up becoming something this intricate, a theory in itself. But nevertheless, there it is.
An ancestor of mine maintained that if you eliminate the impossible, whatever remains, however improbable, must be the truth.
For those people who insist, however, that the only thing that's important is that the theory agrees with experiment, I would like to make an imaginary discussion between a Mayan astronomer and his student. The Mayans were able to calculate with great precision the predictions, for example, for eclipses and the position of the moon in the sky, the position of Venus, and so on. However, it was all done by arithmetic. You count a certain numbers, you subtract some numbers, and so on. There was no discussion of what the moon was. There wasn't even a discussion of the idea that it went around. There was only calculate the time when there would be an eclipse or the time when it would rise, a full moon, and when it would rise, half moon, and so on. Just calculating only. Suppose that a young man went to the astronomer and said, I have an idea. Maybe those things are going around, and there are balls of rocks out, like rocks out there. We could calculate how they move in a completely different way and just calculate what time they appear in the sky and so on. So, of course, the Mayan astronomer would say, yes, how accurate can you predict eclipses? He said, I haven't developed the thing very far. He says, but we can calculate eclipses more accurately than you can with your model, and so you must not pay any attention to this because the mathematical scheme is better. And there's a very strong tendency of people to say against some idea, if someone comes up with an idea and says, let's suppose the world is this way, and you say to him, well, what would you get for the answer for such and such a problem? And he says, I haven't developed it far enough. And you say, well, we have already developed it much further, and we can get the answers very accurately. So it is a problem as to whether or not to worry about philosophies behind ideas.